I thank you for coming on this foggy morning. So I would like to encourage you to come closer because this is going to be very hands-on. So and I'm going to show you some demos. This is the demo day. I have about 3 demos. So first of all, I should tell you that I see completely different colors on my laptop. So the bar that is highlighted is orange on my laptop. So if there's something you can't see very well, I can describe it to you. But let me know. So if you remember, last time I stopped midway through this part. So I'm going to make a short recap. So what did we talk about last time? The subject was how to build a system which allows you to program a cluster as if it was a single computer. And we built this system using a series of software layers. We started at the bottom using simple machines. Then we put on top a deployment layer which manages those machines, installs software, reboots them. Then we have the cluster services which specialize those machines. They installs various types of applications like name service, scheduling, remote execution. Those services allow you to tie the machines together in a cluster. Then we talked about how to build a huge disk out of many little disks, the ones present in the machines. And we saw that the core idea is that each machine contributes the disks, and then files can span many disks. And there's a file name service which tells you where the pieces of each file are. And then the core idea of the file service is that files are so big that you can't even read them anymore. So what you do, you send your code to wherever the pieces reside, and the code accesses the files locally. And now we reach the stage of execution, where we're talking about how to run programs on a cluster. And I'm going to remind you, we talked about this software that we call Dryad, but it's a very generic idea. It's about data flow execution graphs. So in Dryad, computations are graphs, acyclic graphs in particular, although there are systems which support cyclic graphs, but not Dryad. And then each node in the graph is one computation, and then computations talk to each other through point-to-point channels. So they read input data, they write output data. They have no idea who's at the other endpoint of a channel. Each computation is completely isolated. And then ideally, those computations should be a deterministic function of the input channels. Whenever you run them, they should, with the same input data, they should produce the same output data. You will see in a second why that's important. And when we saw that those computations are virtualized, you can use multiple machines to execute such a distributed graph. All right. So we were left somewhere around here. So this is the slide I stopped at. So one point that recurs through this presentation is that you use cheap machines. Because they are cheap, they will break. So if they break, your computation will make no progress. The more machines you have, the higher the probability that at any moment some machines will be down. So then you have to handle failures. And then it's very easy to handle failures if your computation is deterministic. And it's also idempotent. That means any number of times you run your computation, you will get the same result. So Dryad distinguishes 2 types of failures. The first failure, a computation crashes. So while you run some computational machine, the machine just goes down. You can't really tell whether the machine is down, or you can't talk to the machine anymore. But the one that decides the computation has crashed is the job manager, or the graph manager. If you remember, there's one centralized machine that manages the whole computation. If that guy decides the machine has crashed, the machine has crashed. So what the graph manager does is it instantiates the same computation on a different machine and runs it again with the same input channels. So because you can run this computation any number of times, you will get the same result. It makes no difference if this guy is still running someplace. Now, there's a second type of failure that could occur, which is a channel failure. A channel failure means, all the computations run fine, but when you try to read your input data, you can't. The data is somehow gone between the moment it was created and the moment you try to read it. Maybe the disk crashed. Maybe the network connection to that machine is down. And in that case, what you do, you backtrack. The graph is acyclic, so you move one level closer to the source, and then you rerun the computation that generated that particular data. And then, because if you remember, the input data is always stored redundantly. So this backtracking will go eventually up to the beginning of the graph for the first layer, the first stage, and there the data should hopefully be available. If that data is not available, you're stuck. But that's why you triplicate the data here. You don't triplicate the data produced in the middle of the graph because you can always regenerate it. So now, there's a very nice story about fault tolerance. So it turns out that fault tolerance sometimes can be a problem. So I have a colleague in my lab. His name is Chuck Thacker. He's a very interesting fellow. He got the Turing Award in 2009 for his work that he did at Xerox PARC in the early 70s. So he actually built a workstation called the Alto. It's an amazing piece of work. If you have a chance to read or see an Alto, please do. So in 1972, the Alto had the following features. It had a bitmap display. Actually, Chuck has the patent for the bitmap display. He built the first bitmap display in existence, where each pixel has 1 bit in the memory. It was unheard of. Prior to that, all displays were vector-based. Then they had Ethernet. They had a mouse. They had what you see is what you get, document editing. They had laser printers. They had email. They had a distributed operating system. This is all in 73. So most people started to use this kind of software only in the 90s. So these guys really created the future. And Chuck has a nice story about the Alto. He said when he designed the Alto, memories were very expensive and very flaky. The main manufacturer for memories was Intel. That's how Intel actually got started, by manufacturing memories. So he actually built in error correction into the memory system. Today, most servers you buy can have error correction in the chips themselves, but at that time you had to build it yourself. So they built error correction, and everything worked just fine. And then a few years later, Xerox decided to actually sell this computer. And they said, it's too expensive, so let's cut some cost. What can we cut? And they said, look, this error correction code is useless. Let's just take it out. We don't need it. They took it out, and the machine stopped working completely. They said, what's wrong? I mean, what's different? And then they went and looked at the logs. So it turns out that every time the error correction system finds a fault, it should log it. But nobody looked at the logs because everything worked perfectly. And the logs were giant because the memories would fail all the time, but the error correcting system would fix the failures and keep the machines running. So this is the danger I'm talking about. Sometimes your fault tolerance can mask failures in some parts of your system. So it looks like everything is fine, but you're paying a cost. So the lesson I want you to learn is that you should always log the repairs that your fault tolerance does, and you should always review those logs periodically. Check the logs and understand whether your system is working properly or not. Another issue I want to talk about is there's many types of failures, and actually that's what makes distributed computing very difficult. So when you program on a single machine, the machine is either up or down, right? There's no other state. So if it's down, you can't use it. But in a distributed system, some parts could be up and some parts could be down. And the trouble is you never know the truth about the other parts. Are they up? Are they down? So that's what makes very, very hard programming distributed systems. This is the fundamental difficulty. And there's many modes a machine can fail. The best way a machine can fail is if it crashes. So it just stops working. This is called also fail stop. And this kind of failure is very easy to handle because you know the guy is dead, so you just give the task to someone else. But there's many other kinds of failures. For example, some machines could be alive, but they could be very, very slow. So you say, are you alive? And they are so slow that they can't even reply to you. Or there's some kind of errors which are called Byzantine. I have no idea why. Byzantine means very malicious. For some reason, the guy that coined this term thought that the Byzantine Empire was full of malicious people. I don't know. And so these machines actually will act against you purposely. Also, another type of failure you could have is a network partition. So all machines are up, they are working fine, but the communication is cut between the machines. So you cannot know whether the machines are up or down. And building a system to manage these failures is very difficult. Each of them should be handled in a different way. So when you build a system, a distributed system, you have to understand what the failure model is. You have to model the failures. For example, very few people model Byzantine failures because they are just too hard. to deal with. And then even this model is usually hopeless, because even if you have multiple machines, a software bug will behave like a Byzantine failure, and then all machines will be affected by the same bug at the same time if they run the same kind of computation. So normal defenses won't help you unless you actually you're willing to write your code twice or thrice. So when you build a system, understand what kind of failures you are accepting, and then that's not enough. After you keep running your system, validate your failure model. So measure if your system is running fine, see what kind of failures you have, and if you have too many failures of an unexpected kind, for example, maybe you design your system for fail stop. This is what Dryad does. Dryad is designed for fail stop, but if you have Byzantine failures, this won't work. Dryad will give you wrong results. So you have to validate your failure model in practice. Right. So let's go back to Dryad. So if you remember, Dryad runs this computation. But Dryad actually has one thing which is very interesting. It actually can rewrite your computation graph while it's running. And I'll give you some examples why that's very useful. So for example, let's say you have a stage. If you remember, a stage is a set of vertices in the graph that compute the same thing. Let's say you have a stage composed of 4 vertices. And they all compute. And for some reason, these 3 are finished, but this guy is not. This guy is still chugging along. It's very slow. So what Dryad does, it actually creates another duplicate of this vertex, which computes on the same input data. The channels come from the same source. And then just makes a race. Whichever finishes first, the guy will win. So this will enable you to tolerate machines which are not fail-stop. If a machine is not fail-stop, but it's just very slow, this solution will save you, assuming they are not you don't pick a second machine which is also very slow, which is very unlikely. This is about the failure model. If you have many machines which are very slow, this solution is not adequate. But the funny thing is that when to create a duplicate, well, how do you know if this guy is too slow? Maybe this guy has been processing much more data than these neighbors. Maybe that it's to be expected for it to take much longer. So one thing that Dryad allows you is to write your policies. You can create policies for duplication and inject them in the program. And this policy can be any function of the running times of the vertices in the stage and also of the data size. So for example, what Dryad does by default, it computes a regression. It estimates the output, the running time as a function of the input size. And it tries to fit a curve to the observed running times. And based on this curve, it tries to estimate how long these guys should take. And if you are 2 standard deviations away from what you expect, that's when you fork a duplicate. But what's nice in Dryad is that it allows you to override this policy. You can write your own policy. Let me give you another example where it's very useful to be able to rewrite the graph dynamically. So let's assume that we have this graph in which we want, let's say, to sum up values that come from all the vertices. This guy should produce the sum. It's the aggregation that we saw in LINQ. So now, what could happen at the runtime is now I labeled each machine with the rack where the computation is running. For example, this guy and this guy, the first and the third guys are running in rack number 1. Now, this guy and this guy are running rack number 2. Now, if you remember, inside the rack, you have much more bandwidth than between the racks. Now, if your computation is associative, what you should do is you should add up values first in rack 1 and separately in rack 2 and separately in rack 3, and then do a final aggregation here. And Dryad can do that. Dryad has this dynamic manager for the graph, which allows you to write code to dynamically manage the graph. So at runtime, for computations which are associative, Dryad will do exactly this. It will create an additional layer of aggregation, and it will collocate. It'll actually, what it does, it affinitizes these nodes to have the same location as the source nodes. So so the problem is that statically, you don't know where these guys will run. So you don't know how to connect to these edges. Who's in cluster, in rack 1, who's in cluster 2. You will know this only at runtime. That's why you cannot create this graph statically before you start computing. You can create this graph only after you've seen where the computations were scheduled. And then you create these 3 nodes, you affinitize them. You say, I would like this guy to run on rack 1 because that's where the inputs are. And the scheduler hopefully will give you a machine in rack 1, and you'll be able to run there. So this is another question of policies. How do you want your graph to be rewritten and where you want machines to run? And this is another lesson which is very important and this is a lesson important in all system design, to separate the policy and the mechanism. So the mechanism is whoever does the action, but the policy decides when to do the action. So you want the policies to be as flexible as possible, although it's not always easy. You want to implement very general mechanisms, and then you want the policies to control those mechanisms. For example, in Dryad, the mechanism is the graph rewriting mechanism. The graph rewriting mechanism is built into Dryad. Dryad can do that for you, and it gives you a series of hooks so you can control it. Now, policies users could write. You can write your own policy to decide when to create new nodes, when to destroy nodes, when to hook up nodes. And that's a policy. So it's ideally, applications know what they need, and they should implement the policies. But it's not easy, because policies are essentially languages. You specify what you want done and when. So you have an API, which is a contract between the application and the runtime, and these languages can become very complicated. So powerful policies are a plus, but such systems are much harder to design and maintain. So this is the comparison. The policy is like the laws. So here's the Moses tablets. The laws that should govern the functioning of the system, whereas the mechanism is the actual functioning of the system itself. So now the advice is that policies should be left at the application level. Try to delay. Don't build a policy into your system. Don't decide, I should do this when this happens. Usually you don't know how your system is going to be used. And then in our system, they can be very complex. And we have good default implementations because very few people can write good policies. And it turns out that the compiler that we run on top of Dryad generates policies itself. So in practice, people never write policies. But the mechanisms are built in. And for example, the scheduling mechanism is built in. The graph rewriting is built in. The fault tolerance is a mechanism that's built in. And statistics and reporting is another mechanism that's built in. So policies sit on top of these mechanisms. All right. So what did we get? By starting from the bottom now, by putting a series of software layers, we have built a machine which is reliable, because the deployment layer makes it reliable, which has infinite storage and infinite machines, because you can run on all the machines in the cluster, and even if the job is bigger than the number of machines, we can still run it. And then has essentially infinite resources, and it's also reliable. We have a reliable machine, because fault tolerance will make it reliable even if there are crashes. All right? So we have a very nice system that we can program. And now I wanted to show you how to program it, but we'll make a break in the flow of the presentation, because I want to encourage you to think in parallel. And the best way I can do this is by playing some cards with you. So let me explain what we're going to do now. So if you look up the definition of computing, so for example, the definition of computer, a computer is, what you would expect today as a machine. But the second definition is somebody who computes, somebody who calculates numbers or amounts using a machine. And I have for you a picture here from the 1930s. The caption of the picture is "Human Computers at NASA Dryden." And these are the computers. You can see these ladies. They actually don't have any machines. They compute by hand. Maybe they use some helpers. So this is what we're going to do. I'm going to make, out of 4 of you, some human computers. Actually, I'm going to need 4 volunteers. It's early in the morning, I know, but this is going to wake you up. Trust me, it's not difficult. There will be no punishment. Maybe you can get some extra credit on the homework. So I need actually, let me tell you how this is going to run. So I have some playing cards. They are just regular playing cards. There's nothing special about them. They will be the input data. So I'm going to give you, this is actually a collection. It's like a LINQ collection. These are the records in the collection. And we're going to do various computations with these cards. Now, we also have some blank cards. These are blank cards. I had to order them specially. They are good for tricks. So these are going to be the output records, which the human computers will produce. So whoever shows up here in front, they will have to bring a pen. So you're going to write your answers on those cards. That's the only way you can communicate, using your records. And then we are going to communicate by exchanging cards between the human computers, and communication is expensive. So we're going to try to avoid that. Now, unfortunately, playing cards, they have a different terminology in every language, and it took me a while to learn it. So in English, they are called clubs, diamonds, hearts, and spades. I don't know how they are called in Russian. But hopefully we'll manage. Hopefully you won't need to remember this for too long. And we're going to use this order. When I say order the cards, the order starts from 2 and then is the JQKA, right? This is the order we're going to assume. All right? So now what I need is we're going to create a Dryad computation graph, but we're going to emulate the machines. So what I need is one graph manager. Actually, the graph manager can change at every problem. And I'm going to need four machines, 4 computers. It's your chance to be a computer. I know it's what you always wanted. We can even turn off the recording. Yeah, please. Thank you. Let's applaud. We have a courageous volunteer. We have 2 of them. Hurry up. The places are running short. There's not much time left. Yes, yes, yes. Thank you. Thank you. Excellent. Excellent. All right. So what I'm going to try to demonstrate to you is that it's faster to compute in parallel, at least sometimes. OK, we need we're going to have a graph manager for each problem. So let's see the first problem. So the first problem is actually very easy. OK. So first of all, you have pens? Everybody have a pen? You don't have a pen? Maybe you can borrow a pen. Maybe I might have a pen, but it's faster for you to get. OK, so these are the blank cards. I'm going to give you some blank cards to write on. Hopefully, they are not too slippery. Hopefully, you can write on them. You should try. Why don't you sign yourself or something? See if it works. You're not going to use too many of them. Does it work? OK, good. So now, this is a full deck of cards. But because we know what's in a full deck of cards, I'm going to take some cards out. So they can't guess, I mean, the answer is obvious. If for a full deck of cards, the answer is, for the first problem, is counting the number of cards. The number would be 52. So, but I took some cards out, and you don't know how many. All right, do we have a graph manager? Come on, it's easy. This is the easiest problem. This is your time to shine. You won't get a problem as easy as this one. You want me to show you how it's done? OK, I'll show you how it's done. But for the next problem, I need a volunteer. So what I'm going to do, I'm going to distribute. This is the distributed file system. It's this table here. Everybody gets a bunch of cards. These are your tuples or your records. All right. So now they cannot do anything. They are just workers. They have a remote execution service. And I tell them, I invoke the remote execution service, and I tell them what to do. All right? So what they should do is each of you count the cards you have, and then write the number down on a blank card. Somebody count the number of seconds this takes. All right? Everybody seems to be ready. Now, hand all the cards to one of you, so to that side. Now what you do, you sum up all those numbers. Add them up and write the result on a card. I can tell you nobody will check the result. So see, this is how it works. This is how Dryad works. There's a guy, the graph manager, that tells the workers what to do, and they do it. See, this part of the computation is not parallel. The first part was very parallel. Everybody had work to do. Now we have a bottleneck because there's only one computer working. So this is how aggregations are in general. Aggregations, they have a tree, and the tree usually reduces the degree of parallelism. She's done. Excellent. So she said 47, right? It looks a little low, frankly. But OK. So now, for a comparison, what we'll do, we'll try to run the same computation on a single machine. So you're going to be my machine. So he's going to run the exact same computation. So let's see if it takes him any longer. Back of the envelope. How many cards you have? These guys are idle. This is wasted money, It's the data center runs and consumes power and, Yeah, that was right. This is bad news. It means I'm missing some cards. No, actually, it's right. It's right. I apologize for mistrusting My fault tolerance was a little too high. I mistrusted. I thought it was a Byzantine failure. Excellent. All right. So which one took longer? Ah, come on. All right. Okay. So maybe you're right. Maybe you're right. The first one took longer. But if I use 2 decks of cards, I bet the first one will be faster. And then if I use 10 decks of cards and I use 10 people, doing it in parallel will be faster. All right. So parallel is not always worth it. But if you have a lot of data, it pays off. All right? So let's say this where the bottleneck was in the last part. All right. Now, second problem. We need a graph manager. So the problem is now I'm going to give them each a set of cards, and I want them to keep only the even cards. So your output will be the same cards, but throw away the odd ones, where the definition of odd is whatever is crossed out. So the previous one was aggregation. This is called filtering. If you did your homework, maybe that's why huh? No, just filter. Just produce a new set. But wait. We need a graph manager. Come on, you saw how easy it is. Excellent. Thank you. All right. So you can instruct them in Russian, but if you do that, you have to tell me what you did because I have no idea. Or you can tell them in English what to do, whichever way you prefer. All right. Well, they have to read the data, right? They have to tell them or pick up your, yeah, but yeah. Yeah, look, we have a slow machine. Are you all done? So, yeah. Oh, are you checking or are you doing it? Unfortunately, it's hard to duplicate cards. All right. So it looks like everybody's done. What did you notice? There was no communication except the control messages. She told them what to do, and they did it, but they didn't have to exchange. And this made it very parallel, right? So filtering is very parallel. So this was easy. Why don't you do the next one too? You can veto if you don't like it. So now, everybody pick up all the cards again. So you have to count how many figures you have. Oh, what did I do? Did I press a key? Okay. All right. So tell me, the figures are the ones with the paintings, right? The J, K, Q, and A. So you have to find out how many figures you have. So you have to tell them what to do. All right. So this is actually 2 steps. One is selecting the figures and then counting them. All right. So they will do a filtering to throw away the non-figures, and then they will each count the number of figures locally. And write them down. This is your output. So use another blank card for that. Okay, when they are all done, you should tell them what to do. Good, good. It was easier. The numbers were smaller. What's the number of figures? Now we read the output. That's correct. I have 2 figures here. They succeeded again. This is a group of very good students. Excellent. Okay. So, do we have another volunteer for a graph manager? Thank you. You did a great job, but be on standby if you can't find anybody else. Come on. Come on, this one is fun. Oh, by the way, I forgot to show you the problem. So this was filter and aggregate. So now what we want to do is to group cards by suit. So what we want is to have four stacks of cards with each color separately. So you're going to see there's a little difficulty in this one. So who wants to do this one? She's exhausted. Come on. You don't do it for me, you do it for her. Are you up to the task again? All right. So first of all, let's prepare the input. So mix the two decks you have, each of you. I'll take the dirty cards so you don't get confused. Wow, look, a Byzantine failure. He said, hello world. All right. Okay. So what's the algorithm for that? No, one by one. That's the first step. And think about it while they do it. By the way, this is the group by operator we learn in LINQ. Right? You group by suit. Okay, what next? We don't want the number. We just want the stacks. We want the cards themselves. Excellent. Okay. The clubs. All right? So, okay, so this is the communication step. Watch this. This is complicated. You tell them. All right. So, do you remember what she said? So, she said, send the spades to him. All right. Next. Wow, this is an autonomous system. It computes by itself. All right. Next. Yes, the number of messages. What's the number of messages? It's still 4. Oh, to separate. Okay. So 4 for each card. You still haven't finished the clubs. You have to do the clubs. All right, so it's all to all. So, but watch out, these messages, there's two types of messages. There's control messages. She tells them what to do. Remember, there's the control plane. These are short messages. They are followed by intense activity and sweating on this side. Once they are finished with the work, now, then when they exchange card, these are data plane messages. These are bulk transmission of data, and there were a lot of those in this particular application because they had to send in a all-to-all pattern. So there should be 16 messages, or maybe 12 if you don't, 12 because you don't send to yourself. All right? So this is a complicated pattern, and we're going to see that graphs, that computations that do this are complicated. So this is the group by pattern. All right. All right. How do you like it? Anybody want to do another graph? Oh. Wherever the TAs are, she needs extra credit for the homework. We are waiting for someone else who wants extra credit for the homework. Yes! Excellent, thank you. All right, so let me mix the cards first, because otherwise it's too easy. This step is not part of the computation. The data processing, I didn't show you how the data gets to the cluster. This is something which is outside of the system. Once you have the data on the cluster, you can compute on it, but you have to get the data to the cluster. This is what I'm doing. Usually the data comes from some online service. For example, search logs, ads, whatever, click logs, applications, purchases, stuff like that. So I'm dumping the logs onto this cluster. For example, the search engine has a batch job which sucks queries and clicks and as logs and puts them on the cluster, and then the clusters are used to compute this data. All right, so now what you have to find out is which cards are missing. This is actually tricky. There's many ways to do this. So you have to come up with some algorithm. There are 5 missing cards, as we established. You have to tell me which ones they are without looking at them. And this is a tricky one. That would work, but you try to paralyze the work. Try to keep them doing most of the work. If they write down everything, then you will have to do the work. Ask. Yeah. They could be this low power state. It's called napping. Excellent. Okay. So he wants to do the group by again. Group by suit. So come on, instruct them what to do. Ah, there's a cache. He's caching the results. Excellent. That's a very good solution. He doesn't even have to upload the computation again. He says, run that program again. All right, so speak louder so people in the last row could hear you. They don't compute anything, but they might be interested in the outcome. Wow, he has even a name service. He knows the names of each computer. I was using just the IP address. 1, 2, 3, 4. All right, now what? Okay, so the algorithm he suggests is everybody find out what you're missing in your own suit and write it down on your on a blank card. I see there's some sub-algorithms happening here. I see some sorting going on. This is good. It's good. That's a way to do it. You could sort, and then when you sort, it's very easy to scan and see what's missing. So sorting is efficient because it's n log n, and then you can do a linear scan. If you try each card, you could do a quadratic algorithm. You probe, do I have the 2? Do I have the 3? Do I have the 4? So normally that would be part of the specification. You would have to tell them exactly how to do it. Or in this case, because this is a dense set of 30 numbers, you could use an array, and you could say, put each of them in a slot and tell me which slots are empty. It's like radix sort, but it's a dense set. So you could do it in many ways. You have to write the missing ones, right? Yeah. I'm worried. He's writing down a lot. What could he be writing down? He can't be missing that many cards.
I was using array.
Huh?
I was using array to identify the missing.
Oh, okay. He's using a different algorithm. Okay. All right. And this is essentially the output that you can consume. Are there 5 missing cards? So the checksum is good. We don't know if okay, let's see. I'm going to double check. Do you miss the 3 of hearts? The ace of diamonds? The 9 of clubs? And the queen of clubs? Why do I trust him? And now the 2 of spades. No. All right, the 10 of spades. Okay, good, excellent. All right, so I think this is good enough Actually, no. Let's do one more. Let's do this one. So let's sort them. We want to sort them lexicographically. Do we have another volunteer? Or we're gonna? Yeah. Thank you. This was a hard one. You deserve a break. Thank you.
Why am I not using more efficient group by methods?
Like what?
Maybe like separating those reds and blues and then the groups.
Yeah. Speak louder. Speak louder. People want to hear you. Okay.
Why the graph manager not use one group by algorithm? Like dividing not in four groups, like one, two groups versus
Well, yeah, and then? So you could divide it to 13 groups, one for each, you could do all the 2s, all the 3s. If you had 13 machines, they would use the parallelism even better, right? So you could do it that way. And you could do group by recursively dividing the sets into finer and finer grain. You could do black and red, and then you could separate the reds into 2. That's also a good algorithm. Okay, so now what we want the cards to be sorted left to right, starting with the 2 of clubs, that's the smallest one, going to the ace of clubs, then the 2 of diamonds, going to the ace of diamonds, and ending with the 2 of spades, and the ace of spades is the largest card. This is the bridge. If you play bridge, this is the bridge order, the value of the cards. If you don't play bridge, don't worry. We have another lecture for that. I think you have too few cards. You're going to be overloaded. See, this is called data skew. So if somebody has too much work, they're going to slow down the whole computation. So it's best if your data is evenly divided. But even if it's evenly divided initially, it might not be evenly divided during the computation. All right. Did you make up a solution? So every one of them does that? All right. So the algorithm he has chosen is everyone has to do a local lexicographic order, which is not easy, but it's doable. Because there's 4 of them. And this could be very parallel. We could use 10 people for that, and they would still work very well, right? So this step is highly parallel. There's no communication. Now, are you ready with the next step? Of course, he has to wait. So the graph manager keeps probing. Is everyone ready? Is everyone ready? And they will report, yeah. Good. So everyone has now the cards sorted. Now what? There was a message loss. The retransmission follows. I see. So obviously he's been paying attention to the sorting algorithm, because this is a merge sort he's going to do now, right? Yeah. So now you have sorted decks. You just insert them in the proper order. This is a linear scan. On the other hand, the parallelism is low. See, we have 2 idle machines. He said sort them. He didn't say separate them. Which ones you don't? Hers or yours? Which ones are not sorted?
I had mistake too.
Huh?
I had mistake.
A mistake?
I mean the input date, the date part.
All right. Okay. So see, this is tricky. Actually, so he chose an algorithm which does a tree of merge sorts. I would have done it differently. But the way I would have done it is I would have sorted them by color again, and then everybody gets a color and then does a local sort. So he did a merge sort. I would have done a range partitioning. So you partition by range. So you group them by color, and then everybody does a local sort. And that would actually keep everybody busy all the time, almost all the time. It's a little more efficient as parallelism goes. So now see, what happens is that these 2 guys, they have a lot of cards. And now the final merge, all the cards will be at 1 person. So the cluster will be underutilized. Is that correct? That's what you're going to do next? All right, so the first node is going to be busy for a while. And after this exercise, we're going to take a break. But let's wait for him to finish. So another disadvantage of this approach is that all the data ends up on a single machine. So if you have a lot of data, it's very expensive. We could sort the data without actually putting it together. If one of them had the clubs, the other one had the diamonds, another one had the hearts, and the other one had the spades, and each of them sorted them, we know that the data are sorted just by going left to right. But we don't have to put it in a single deck. It could be in 4 separate decks. And then we use the storage more efficiently, and we use the machines more efficiently. Don't worry, it's very good. I see. So he optimized the number of messages. There's fewer messages sent that way. There's just an aggregation tree which has a linear number of messages, whereas if you do the group by, you have a quadratic number of messages. But the volume of data actually is larger. The messages are larger in your case. Yeah. Excellent. Thank you. You've done a great job. Okay, so now they deserve a break. We'll let them go and refresh, and then I'll see you in 10 minutes. This is for you. Thank you. The applause, I mean. It looks to me like the distribution of the room has shifted towards the back. I promise you there will be no more volunteers, so you can relax now. So now we are at the final, oh no, we have 2 more layers in our hierarchy. This will be mostly demo based. I'm going to show you how things work. So what will happen is that now everything will click together. So all the things we've discussed will assemble and will get a useful running system. So the next stage is called DryadLINQ. Again, DryadLINQ is a project I worked on, and I'm not selling you DryadLINQ. I just want to show you the principles behind it. If you want to use DryadLINQ, you're welcome, but it's just about how things should be done. So DryadLINQ is actually a combination of 2 things. One is Dryad and one is LINQ. We didn't have much imagination in the name. So LINQ, you should already know if you've done your homework or if you listened to me last time. And Dryad is this distributed execution. So what we'll do, we'll put them together. So what we have is we have a distributed execution. This is Dryad, and then we have computations on collections. So what we want to do is want to compute on distributed collections. And then we have DryadLINQ. So now the nice thing is that, so this is how we are going to use distributed collections. So actually, the way the students worked on the cards should give you a hint. We take our collection of data, and we chop it into pieces, and then each machine has a piece. So what the nice thing about this is that this is a collection of collections, and each part is called a partition. Let's call it a partition. But the nice thing is that the parts are also collections. So now we want to compute on the big collection, but we are going to compute on the little pieces instead. And by computing on the pieces, we achieve computing on the global part. So this is cool. Both the whole thing is a collection of type T, and each part is a collection of type T. So there's this nice mathematical duality between collections and collections of collections. So now we're going to take LINQ, which you programmed on a single machine, and by interposing a compiler, seamlessly it's going to run on a cluster by generating Dryad jobs. How are we going to do that? So this is the LINQ program I introduced last lecture, which had 3 parts. Remember, it had the pink, which is the collections. So now the collections, they will just become distributed collections. So the input collection will be here, stored on this distributed file system, and the output collection is this one. It will be stored also on the distributed file system, chopped into pieces. Now the second thing we do, we take whatever query the user writes, like this where followed by select, and then from that we'll generate a Dryad computation. And finally, the key is these user-defined functions, the yellow ones. We actually don't need to parallelize those. We only parallelize the query. These will send to each machine, and each machine will run this code. This is the instructions that the graph manager was handing to the students. These are not parallelized. Each student will run the same instructions in parallel with the other ones. Now, it turns out that DryadLINQ is a research project which has been implemented at least 3 times or 4 times. And we actually did 3 code releases. Each of them made the previous one obsolete. Unfortunately, none of them is really good. So initially, we made an academic release which only ran on Windows HPC. Then we made another, there was a product group created to ship DryadLINQ. And they actually worked on it for 2 years. And the project was canceled the day it was supposed to ship. And then this is the final version of DryadLINQ, which we now released using an Apache license. And you can find it on GitHub. So I don't want to encourage you yet to use it because it still has some bugs. So this one actually runs on top of the Hadoop Yarn infrastructure. So Hadoop, if you don't know about Hadoop, don't worry. It doesn't matter too much. But Hadoop is being rewritten to have a more Dryad-like runtime inside, and it's called Yarn. And it turns out the DryadLINQ, we port it to run on Yarn. And as I said, it's on GitHub at this URL. So right now, there's no installer. The debugger is missing. There's a lot of missing features. But hopefully, I'll convince you it's a nice enough tool that maybe you'll want to spend some time with it. So, but what we'll get out of this is essentially now we'll have we can program a cluster using .NET and LINQ, and we have essentially an infinite machine. And the way I want to show you this is by running a demo. So actually, what I've done, hopefully the network, now I need a network. So if the network doesn't help me, we won't be able to do the demo. So this is actually a remote desktop to a machine that I have on my desk in California. So the screen refresh is going to be a little slow. But the reason I need to run it there is because the cluster is in the first floor of our building where I'm going to run this. This is a small cluster, and I'm going to run it on small data sets because we don't want necessarily to benchmark performance or see how much data we can process. We want to understand how it works. So this is actually a Visual Studio. It's Microsoft's tool for writing programs. And it's just no changes. It's as you buy it, I just installed it. I didn't make any modifications. The only thing you have to do, if you want to use DryadLINQ, you have to add a special library called LINQ to Dryad. And then you can suddenly write DryadLINQ programs. So in the interest of full disclosure, I'll show you what I'm hiding for you. So I'm hiding some files. Wow, this is really slow. So these are the files I'm going to use for my program to feed for the input. Then the show on console function, you saw it. It just takes a collection and writes it on the console. Can you read this? Is it too small? In the back. Can you see this? Can you even hear me? I saw someone nodding. All right. And then there's some configuration stuff. So the configuration stuff only sets some global variables to specify, what cluster I'm going to use, what kind of scheduler, and blah, blah, blah. It's completely uninteresting. And then this is the main program. The main program is going to configure the cluster by calling this configure function. And then we are going to compute on collections. All right. So now this is a collection. And the collections are stored in those partitioned collections. We call them partition tables from databases. So this is a partition table stored in this file. It's a small file. And this is the type of objects inside. It's called line record. So line record, don't worry about it. It's not a C# type. It's a type we invented, which just stands for a line of text which ends with a new line. Right? So this means essentially that this is a text file. It's an ordinary text file. And then each line will become a record, one object in our collection. So this is a collection of lines. And then what I'm going to do first, I'm going to just iterate over this table. So the first thing I'm going to do is very simple. I take the whole table, I assign it to the result, and then I show the result. So I'm going to compile this program. Now I'm going to run the program. Now the result of running the program is in this window. So this is a Latin text. Whoever did Latin in school can appreciate the depth of this wisdom. It's actually from Cicero. But this is besides the point right now. This is a small collection, but what happens is this collection actually resides on the cluster. It's on the cluster file system. But this window is on my computer. So what happens is that the file system provides an iterator interface. So now, when you run this function show on console, the data is on the cluster, but this V, for each V in data, the V is on my machine. So I can print it on the screen. So see how easy it is to read something from the cluster, you just say a for each. And you get each tuple, and you can do whatever we want with it. So that's how you access data on the cluster. This involved no computation. It involved only transfer of data. All right. So now we are going to start computing on this data. So the simplest thing you can come up with is counting, right? So see, because this is an IDE, it has this completion, it has type checking. So for example, we know that the result is an integer. And now what will happen is that if I try to compile this program, the computer gets upset because the show on console function expects a collection, but counting gives you an integer, right? So you can't call a show on console with an integer. So type checking is very useful. And notice that I didn't invent the language LINQ. The language LINQ is pre-built for me. I'm just compiling it for a cluster. So all the type checking is done for me for free. I didn't have to write one line of code for this. If you don't know what type checking is, don't worry. It just makes it easy to write programs. All right, so now I'm going to run this program, okay? So the program only counts the number of lines in this collection. So I press F5, which is the debug button, really. What happens is you see in this window, there's a log that starts scrolling. But more interestingly, I can look at this web page. So this web page is actually a live view of my job. So this is actually a Dryad job that was generated from the LINQ program. This is the input file. This is the output file. There was a temporary output file created. And this is two processes. These are the point-to-point channels that I told you about. So what this guy did, this guy read the input file and parsed each line into a record and then counted the number of records and sent the number of records to this guy. This guy did nothing. And then the output was written here. And now if you look at the window, the number of lines was printed here. Unfortunately, the screen is very small. The number of lines is printed here is 28. So this is a small file. But see, I just press the button and I run a computation on the cluster. So let's try to do something a little more interesting than just counting the number of lines in a small file. So we'll count the number of lines in a big file. The file is not huge. The point is not to compute quickly, but to see what happens. So see, the only thing I've done is I've changed the file from a small file to a big file. Now I'm compiling this program, and I'm going to start to run it, and I'm going to open the web browser. So let's look at this graph. So what happens is this file actually has 10 partitions. These are the 10 partitions. And what you see here is the color of the nodes show you that there's a finite state machine that the graph manager maintains for each node. The finite state machine has the colors here: failed, completed, running, waiting, and uninitialized. So you can see how this computation makes progress. It's very quick because it's a small input file. But each guy reads the lines in the file, then counts the number of lines, says the number of lines to this guy who aggregates them. So this is very reminiscent to what the students did initially when they counted the number of cards. It's exactly the same program, but run on a cluster, right? So now let's try to do some, what I'll do a few of the exercises that you've done in your homework. Actually, I've done actually all of them, and I could show you how they look. They are kind of funny. Sorry, that's not what I have to do. I have to be very careful what I type here because the feedback is very slow when between clicking a button and all right. So now what I want to do, we counted the number of lines. I wanted to count the number of words. So that was, I think, your first exercise. You should know what this means. So I take each line and I split it into spaces. Let's not be too fancy. And then I get a collection of words, and I'm going to count these words. All right? This looks good. So let's compile this program. And now let's run the program, and let's look at the window while it's running. So the program has the exact same shape, because the compiler is smart enough to ask these guys to do two things. Actually, three things. They read the lines and parse them. They split them into words, and then they count the words. So there's some pipelining here. In one computation, there's actually a little graph inside which does three things. And they send the counts to this guy adds them up and then writes them to a temporary file, and then they show up on the screen. And if you really want to see, it's like 8 million, almost 9 million lines in this file. Okay? So now, another problem you had was to count the number of distinct words. So what I'm going to do is I'm going to use a group by. It's not the most efficient way to count words, but it's simple. So what I'm doing, I'm grouping all the words with the same spelling together. So now let's see what will happen. So if you remember, the group by was very difficult for the students because there was a lot of communication. So let's see how the cluster will manage this issue. So now let's look at this picture. What we get is actually this all-to-all pattern. So the trick that we use here is deterministic hashing. So everybody at the top will hash the word, use a deterministic hash function, the same for everyone. And this, depending on the hash value, we'll send the word to one of the machines in the second row. For example, all the words I will be here. All the words the will be here. All the words you will be here. And then each machine now can count the words locally. And because we know they have different hashes, the words must be distinct. So if you just add up those numbers, you get the total number of words. So this pattern is called shuffle, right? And the trick is to use this deterministic hashing. There's a lot of communication. This could overwhelm the network if you exchange a lot of data. And then you can keep doing stuff. For example, another problem was, oops, I think I pressed the wrong button. Then I ask you to find the most frequent words. So let me align this, although editing this will be very painful. All right, so now I wanted to find the most frequent words. So I group the words and then I will count the size of each group. So I take each group and from the group I create a tuple. Right? So from each group I take the key of the group and the number of elements in the group. This gives me for each word how many times it appears, and then I'm going to order them. So watch how nice this is, because I haven't even finished typing my program, but the compiler knows that this object has a count field because I typed it on the line before. So it's very easy to write correct programs. You won't make too many bugs. Actually, I think we want to order them by decreasing the important ones first. Oops, very hard to type with a slow network connection. And then we'll take the top 10. So now, actually, I'll have to do one more thing. I'll have to convert those to strings for a technical reason. You can't actually output anonymous objects. These are something called anonymous objects. And the serialization doesn't work for those. So I'll just convert them to strings. Don't worry about this. It's not important. And now, because the output is now a collection, is no longer a number, I'm going to use the show on console function. All right? So this just tells you the most frequent words. So let's run this. And actually, this will be a nice program. The program looks similar. What the computer does is actually, first it does the group by, as you would expect. So distinct words are on distinct machines. Then it counts the size of the groups. And then each group only sorts them locally and only sends the top 10 sizes down. So this guy only sends the top 10 sizes, and this guy does merge sort because it only needs to output 10 values. You never need more than the 10 largest from each machine. And actually, even the groups are not built completely. You don't need to send all the does down here and count them. The group by is actually split into an early computation. These machines, they will say, I have 5 does. This will say, I have 9 does. And this guy will say, 5 plus 9, I have 14 does. So it turns out that less and less data flows through the network as you go down in the tree. So by the way, this is also called MapReduce. So if you look, MapReduce is essentially a select, or the select many I've done, followed by this group by, followed by an aggregation step. Actually, it's really a select. So when you read about MapReduce, this is MapReduce. You can implement MapReduce in LINQ using 3 statements. So it's easy. You don't need a special programming language for writing MapReduce programs. You can use LINQ. But the beauty of LINQ is you can write much more than MapReduce. So for example, look at this program. I'm gonna instead of taking, oops, I still have to stop. The program is waiting for me to press a key. Right. So instead of taking only the top 10, I'll sort the whole output, and you're going to see that the plan generated by the compiler will change dramatically. All right, so watch this. This is a nice plan. And this actually, now I'm doing sorting. I'm doing what I asked the students to do in the last step. I asked them to sort all the cards. So this is a much more complicated plan. And this actually is a clever plan. It uses sampling. So what happens is in the first two stages, we do the group by because we want to count unique words. And then what happens is these guys, each of them will sample the input set they have by using some random coins. It turns out that you can use a very small sampling rate. If you get about 1,000 values here, it's enough. Now, after you sample, you send all the values to this guy. And this guy actually computes a histogram of the values in the input set, actually of the samples. And based on this histogram, we now have a distribution of the input data. And why is that important? Because you could have a lot of zeros and you could have very few fives and hundreds. You don't know how to send the data around. But we take this histogram and we divide it such that there's equal volumes under in each cut. And then we distribute this histogram cut to everyone. And these guys again read the input data entirely. And what they do, they do a range partitioning. They redistribute the data to these guys such that this guy gets all the zeros. This guy gets 5 and 100. This guys from 100 to 200 and so on. So this split here is done so that everybody has about an equal amount of work based on the observed distribution of data. And then after these guys get the data, each of them sorts it locally. So it's like the algorithm I suggested, but we didn't do with students, where we divide the cards by color, by suit, and everybody would sort locally. And now this output collection, see, it has 10 parts. This output collection is the sorted collection, if you read it from left to right. We don't need to put it in one place. We know it's sorted. It's good it has 10 pieces. It's much faster that way. All right, does it make sense? All right, so let's see, how are we doing for time? I still have a bunch of nice demos. What I want to show you, so I have your homework. Let me run your homework for you. Actually, I didn't run all the programs in the homework because some of them are just stupid. And then I changed them slightly. So one thing I changed, for example, is some programs output very large sets, like they output the whole matrix. And there's no point in printing a large object. So what I do actually, for example, for the matrix, I count the number of non-zero elements, and for the graph algorithms, I count the number of reachable points, and I only take the top 10 page ranks. Okay. So when I do this, it will run a sequence of 10 programs out of the 12 in your homework. What I didn't do the Cartesian product. You should never do a Cartesian product of two large sets because it's very large. And I skipped another one. I forgot which one. Actually, this is problem 1. So actually, this is kind of pointless because we have already done this. I should have just skipped it. So this is problem 1, which was the number of words. This is the problem 2, was the number of unique words, is the same group by. Let's see, how can we do this so we can see everything. Let me move this window a little. All right, like Moscow, real estate on the screen is very expensive. So the third problem, I completely forgot. What was the third problem? Did anybody do the homework? Oh yeah, the top 10 words. So this one we have also already seen. This time they are running on a larger collection. They are not running on your test data. But the point is, and these are the results here, the top 10 words with their frequencies. The fourth problem was, I think, to find, I forgot what the fourth problem was. Anybody did the fourth problem? Oh, yeah, the vowels. So for the vowels, I changed it slightly. I just counted the number of vowels. So we extract vowels and then do a group by vowel and count them, because you don't want to see such a large set. All right. Now the fifth problem was finding a set of words. So this is actually an interesting problem because it has two inputs. It's a join. So this is actually a join between two sets, one of which is small and one of which is large. So the pattern used for joining is actually a generalization of group by. So this is the small set, this is the large set. They are both hash partition on the key that they are going to be joined on. And then because they are hash partition, then we do a local join on each machine. And then we know that there are disjoint keys on each machine. So if you don't understand what I'm saying, don't worry too much. It's cute. So it turns out the join and group by are essentially the same thing, except one has 2 inputs and one has 1 input. Now, problem 6 and 7 I'm skipping because I thought they were stupid. But it's not all right to skip them in the homework. Now, problem 8 is now the, what was problem 8? Was something with the, is it a matrix already? This, yeah. So problem 7, I remember, was the max element in each line in a matrix. Now, this is for this is the transpose of a matrix. So the transpose of a matrix is trivial. It's just a select. And then after the select, I also counted the number of non-zero elements, and it's 10,000 non-zero elements in this matrix. It's actually an almost diagonal matrix. It's 5,000 by 5,000. So now the next one is adding to matrices, and adding is done using a join. If you haven't done your homework, you should quickly write down what I'm saying because this is the solution. And it's a join, and I'm adding so you concatenate two matrices, and then you do a join on the coordinates, and then I'm also counting the number of elements. And then the multiplication is even more interesting. It's also a join. So you repartition the matrices so that the rows and the columns fit, and then this machine will get all the rows, row 0 from the first matrix and column 0 from the second matrix, and we'll do the multiplication. We'll do a dot product essentially. And again, here I'm counting the number of elements, and I'm printing only that. And then now this is the graph problem. This is the graph reachability problem. It's 5 steps. How many nodes can you reach starting from node 0? And you can actually see the 5 steps. This is step 1, 2, 3, then 4, 5. So you can see the scheduler running nodes in parallel. When a node has no inputs available, it has to block waiting for the other nodes. So you see that the graph shapes can become quite complicated. So this is 5 iterations run in a single computation. My connection is kind of choppy to California. All right. And the last problem was the page rank. So I'm going to run 2 iterations of page rank, and I'm going to only show you the nodes with the top rank, the top 10 nodes with the top rank. So most programs were a few lines of LINQ. This is 5 times like 3 lines of LINQ. So you take 3 lines of LINQ and put them in a for loop, and you get this program. So one thing that you should notice is that I never specify how data should be sent on the network. Because these programs are type safe, the compiler knows the type of every value that is going to be sent around when it compiles the program. So the compiler also generates automatically code to write this data to disk and to read it from disk. So it's very efficient. We generate very efficient. This is called serialization. The data has to move between machines. So this is 2 page rank iterations. The page rank involves a join. So there's one join here and there's another join here. So you join the nodes with the edges based on the endpoints. So this shows you that you can write stuff in LINQ. Okay. So and it's easy. You know, I took your homework, the solutions I prepared for your homework, and I changed a few things to make them output small results, and I ran them on a large data set. That's all I've done. So the programs you can write to run on a single machine, most of them will run on a big cluster as well. And okay, this is the whole homework. But not any LINQ program will generate an efficient plan. So it's not enough to know LINQ to write parallel programs. You have to think in parallel. And this, the goal of the exercise we've done together is essentially to show you how to think in parallel. You saw that some algorithms are better than others. So merge sort is less efficient than range partitioning followed by local quicksort. So that's one of the messages I want you to remember. So, and, okay. So that's about it. So let's move back to the presentation. So I had some slides in case my demo wouldn't work. So let me mention a few funny things. One funny thing is that if you look, what happens is you have your query, you use DryadLINQ, you compile it, each machine now computes on a small collection. You can recurse. This collection you can split and to cut into several little collections, and each of them runs on a separate core. So this compiler actually parallelizes twice, once across machines and once across cores. So if you look at the processor utilization, we can use all the cores in a machine very efficiently if we have enough data. And it's the same language. So we compile LINQ to LINQ, and then again LINQ to LINQ. So we compile LINQ on a cluster to LINQ on a machine, and we compile LINQ on a machine to LINQ on a core. It's cute. And I had a bunch of other deep wisdom. Maybe I'll spare you this. So let me tell you about a few applications we built on DryadLINQ. So first of all, we built some tools so you can visualize jobs. This is run on big clusters. You have to understand what they're doing, so you can see the graph, the vertices. It turns out, how do you debug this kind of program? Actually, I have a nice demo about debugging too, but I won't run it for you. Because these programs are LINQ programs, you can run them on a single machine as well. And you can just use the debugger. If you run it on a small data set, you can use the debugger and you can just inspect the values using the built-in debugger. It's very easy. But if you run it on a cluster, you can't do that. And the way to debug programs on a distributed system, I only know one, which is printf, or actually logging. So you have to log everything. Everything that's important, you log. For example, this is a log generated by one of the computations. And then if you need to debug something, you go and look at the logs. The nice thing about the logs is they are there. Even if you have a transient failure, the logs will tell you what the failure is. But of course, you can't log everything, because at some point you have more log data than you have actual useful data. So it's a trade-off. But at least, for example, the graph manager, which is this guy, will actually log all the state transitions of the vertices. Whenever something transitions from started to failed to running to so on, there will be a log line, and that's used to build this visualization. And then if you have the log data, you can build all sorts of funky stuff. For example, this is a timeline. This is time, this is machine, and this is stage. So you can see how a job ran on a cluster. And this yellow line, which looks green here, is the critical path. So if you see this is DAG, the longest path in a DAG, each node has a length with the time it took to run. This is the longest chain of in the execution DAG. And this is why you waited. So this guy actually made everyone wait. So when white means machines are underutilized. So you can go and debug your stuff. And you can plot nice graphs. For example, we log the CPU utilization. So this is the CPU utilization across the whole cluster for this job. And each color is a different, it doesn't matter what it is. All right. So now I want to change pace, and I want to tell you about one application that I worked on for this system, which was very cool. Actually, I don't know if do they still Kinect in Russia? Does anybody have a Kinect? Oh, hey, good job. Well, everybody else gets a free one. No, just kidding. Just kidding. Unfortunately, I don't have the power to do that. I would like to. So I brought you one to watch. So let me tell you about Kinect. So this is already old news. This has been already around for 3 years. But I think it's an interesting device. And this is actually a very cheesy video, but I don't have the sound hooked up. So do you know what the Kinect is about, or should I play this video for you? Yeah, so I'll play the video, and I'll also tell you. There's a lot of nice music with this video. So the Kinect is essentially a toy, but it turns out to be a toy which is very useful. Many people find it useful. It's this toy. And it's supposed to allow you to control your Xbox or your game console without buttons, just by gestures. And I'll explain a second why. So what you do is you move your body, and the Kinect tracks your body and then allows you to control stuff on the screen. So this is how it works. But okay, I think this is good enough. All right. So the Kinect is essentially an input device. And it's a nice input device. For the price, you pay about $100 and you get a lot of stuff. The new generation that's coming out will be more complicated. This is the old generation. So probably this is the last time I can give this talk, because I haven't worked on the new one. I only worked on the old one. So it has two cameras. This is a normal webcam, and this is an RGB. This is an infrared camera, and this is actually an infrared laser, which projects a bunch of rays. You are being irradiated as we speak. Expect a nice suntan when you go out. And then it has a motor to tilt it, and then it has 4 microphones at the bottom. So by the way, I'm not trying to convince you to buy this or anything. I think it's just cool. So, and then you're going to see there's a connection. So now, once you have this device produces several data streams. So it produces an audio stream, from the 4 microphones. Actually, it produces 4 audio streams. They are synchronized. It produces 2 streams, video streams. One is what you would expect from any webcam, and the other one is called the depth stream, in which each object is colored according to the distance to the sensor. So see, this guy is bright because he's closer, and then she's a little darker, and then the background is dark, completely dark. So what's the point? The point is that if you try to play the Xbox, and I actually have one because I have a son. I didn't buy it for myself. I bought it for him. You know, I'm a good dad. So this is really difficult to master. It has like, I don't know, 20 buttons. You would think it's easy, but it has a lot of buttons and modalities. So it's very hard to use. What you want is to replace the controller with your body. By moving around, the system tracks your skeleton, and then that's how you interact with the games. Okay, so let me tell you how it works, because that's the interesting part. So if you look at the infrared laser, it actually goes through a diffraction grating, and it projects this image. This is a photography done in infrared of a wall in front of the Kinect. So I'm in front of the Kinect, and this is what's being projected on top of me. This is a fixed pattern. It doesn't move. So now what happens is that if you put objects, if you project it on a flat wall, you see what you just saw. But if you put objects, the pattern will be distorted. For example, here you can see a book, right? Your brain is clever enough to make out a book here. So you do some triangulation because the rays come from a different angle than the sensor, and then the points shift. You see the points shift a little to the right? So this shift will tell you how far the object is. So you can compute how far everything is. So now you have this image coming from Kinect. This is all done in hardware. There's a chip that does that. Now what you want to do is, the body tracking problem requires you to find out where the people are and what they are doing. So that's what we want to do. We want to run the body tracking algorithm on the Xbox, and we want to find out what the people are doing, and then based on that data we want to control a game. Now this wouldn't be maybe too difficult, but it turns out that the Xbox they made this for is really old. It's been done like 7 or 8 years ago already. It has only half a gig of RAM. The chip is fast, but has actually 6 cores. But the graphics card is weak. The trouble is, if you want to do just tracking and vision, it's easy. But the trouble is you have also to do gaming. You have to let the game run. So you have to do both gaming and tracking at the same time. So that's difficult. They were given a very, very low budget, computational budget, to run this algorithm. So this is just the art of compromise. You have to do a lot of compromise. And now, it turns out, by the way, I'm not claiming credit from all this stuff. There's a lot of people that worked on this. I only did a little piece. So this is actually how the vision pipeline works. So you start with the sensor here at the left, and what you get is a point cloud. You get a depth map, which is really a 2.5D, because for each point you see how far it is, but you don't see behind people. You only see the front. It's like a shell. Then you eliminate the background. So first of all, you try to guess where the floor is, the floor plane. And then you eliminate the background by some thresholding, and you also segment the players by some clustering algorithm. So for example, we know we have 2 players. Then the hardest part comes, it's here. You have to label each part of the body. So there's a classifier that runs in real time and tells you for each pixel where it comes from. So for example, this is head, this is chest, this is the left hand, the right hand. See, they are differently colored, and legs and so on. There's like 30 body parts. And then once you know the body parts, you use some clustering algorithm again to find the centroids of the body part. This tells you the pixels, but this tells you where the body parts themselves are. You know, the chest is where all the white pixels are. And this is very noisy. If you look carefully, you will see there's a lot of noise. But the clustering is very robust. And finally, once you have the centroids, you can build a skeletal model, which is a rigid skeleton, and it has some kinematic constraints. So the endpoints have to be attached to each other. It's a tree, really. It's a tree representation. Well, the funny thing is all this stuff up to here happens frame by frame. So we do it in each frame 30 times a second separately. We don't keep any history. The only part that has some history is tracking the body. And let me show you actually how it looks. So I'll stop this again. That's why I brought the Kinect. So this is the demo program. You can't buy this in the store. This is now running here locally. So what do we have here? Let me step in front of the Kinect. Yeah, so unfortunately, controlling the motorized tilt is not, you need a program for that, but let me see if I can adjust it a little so I can fit in the frame. All right, So you have, what you have here is 4 video streams. This is an RGB camera. This is the depth stream that you can see. This is me, you see, in real time. Now, this is the classifier labeling me. It's a little confused by this bench here. So maybe if I turn it around a little, it will be more robust. It thinks there's someone, okay, now it's pretty robust. It got me, right? So I can move and it will tell you in real time what each of my pixels is. And finally, based on this data, this is the interpolated skeleton. Unfortunately, the Bolshoi was closed. I wanted to visit, but there was no show during my stay here. So this is the only thing I can offer you. All right? So this is how it works. So it works in real time. This now runs on my laptop, but the same thing happens on the Xbox. All right? So let me tell you a little more why I'm telling you all this stuff. So the part that I worked on was this, going from the depth map to the labeling. And then this is done by a classifier. So each pixel goes to this classifier, and the classifier will tell you, yes, I think this is a head, I think this is a hand, this is a chest. And the only information the classifier has is the distance from the point to the camera. It doesn't use the video stream. The reason is that it's very sensitive to illumination, whereas illumination is insensitive because it has its own laser. And this runs on the Xbox GPU. So they actually knew how to run this on the GPU because the CPU has to be used for the games themselves. So now the question is, how do you know what a human is? It turns out that there's a huge variety of human shapes. So I ask you, go home, write me this is the next homework for next time. Write me an algorithm to recognize the shape of a human and tell me which one is a head, which one is a hand, which one is a leg. And I think you'll have a lot of trouble because there's a lot of variety with body types, hair, clothes, the angle of the camera, there's also pets, there's furniture. It's a very complicated problem. It's not easy to do it like in LINQ. LINQ, compute on numbers or cards, but this is a very ill-specified problem. So how are you going to solve it? And the question is, how do you recognize a human? Because you do recognize a human. I showed you a human, you would be able to tell me perfectly. Anybody have any idea? How do you do that? Come on, venture a guess. Louder. Yeah, but that's not enough. That's not an algorithm. It's a word. Well, the truth is actually you learned it by example, right? So when you were very little, you actually saw a lot of labeled examples of humans. They would come to you and they would say, this is your father's nose, right? You don't see that many labeled examples. There's a lot of unsupervised training as well, but you need some labeled examples. But this is how we humans learn. If you think about it, it takes you maybe a year. Well, you start speaking around 1 year old, right? So 2 years you speak seriously. So maybe you can recognize it sooner. But it takes you a lot of time. You see a lot of examples. So that's what we did with the Kinect. We said, we don't know how to describe a human. Let's just learn it from examples. So what we did, we created a lot of examples. So this is the depth map the camera is going to see. And this is the labeled, the correct interpretation of the body. So now what you do is you take lots and lots of those, lots of examples, and what you feed them, you feed into a machine learning algorithm. This is how machine learning looks. If you never saw machine learning, it's a set of shiny pipes. And then the machine learning, the nice thing is it takes a lot of images, and then what it comes out is a little drop of wisdom. It's like the liquid that alchemists were looking for. And that one is called the classifier. So the classifier is the smart guy. The classifier is built out of a lot of data, but it's actually quite small if you look at it. But it synthesizes a lot of data. The same way your brain learns a lot from a lot of examples, but synthesizes a small algorithm inside. Right? So now where do we get the examples? I don't know if you saw this movie. It's actually okay. It's an okay movie. So the examples actually, we know how to generate them. The movie industry has been doing this for like a long time. For example, these two guys, they actually digitally generated from these two by using a nice technology called motion capture. And actually, we rented a studio in Hollywood initially, and then they built their own studio at Microsoft to do motion capture. And for example, there's 2 ways to do motion capture. With lights, or this is with the electromagnetic fields. But the point is, you label the body parts, so you have the ground truth. You know where each light is. And then you ask the actor, this is an actor, you ask them to move around, and you record the position. So what you get you get a set of avatars, and then you distort the avatars. So let's say the actor was this guy, and then you distort it according to body shape. There's, females, males, children, and children are not just scaled down adults. You have to record children too. They have different proportions. And these are the 8 avatars with the correctly labeled body parts. And then the avatars, you ask them to move around, and you record them in a lot of positions. So, this is a pair. These are pairs of training data. Depth map, this is the input and this is the output. Input and output, input, output, input, output. This is what you want to learn, the map from this input to this output. But the trouble is the camera doesn't work that well. The camera has a lot of noise, if you looked at the camera I showed you. So before you learn, you have to induce noise in the data, because if you learn on perfect data, you will get garbage when you look at the real data. So you have to have a model for the camera noise. So see, this is all engineering. In principle, this is very simple, but there's a lot of stuff you have to take care of. And now, it turns out that the classifier that was used is a very simple classifier. It's a decision tree. I don't know if you probably know about decision trees. If you don't know, don't worry too much. So let me explain how the decision tree in Kinect works. So we're going to classify the pixel on here, which is happens to be hand. So what we do, we take a window around the pixel, right? And now what we're going to do, we're going to look at a few other pixels. For example, we look at a displacement, the green displacement. And we look at this pixel, and we see, is this background or is this body? Is this background or is this body? What's the distance in depth between those two pixels? And we make this comparison of this green node. And if the distance is smaller than a threshold, we go left. If it's bigger than a threshold, we go right. And then when we go, so see, we went right. Now we take 2 other pixels, and we look at them and say, how far are they in depth from the camera, these 2 pixels? And again, we do a threshold and so on until we reach a leaf. And at each leaf, now we have a probability distribution which will tell you, oh, if you reach this chain of events with probability 60%, this is the left hand, with probability 5% is the head, and so on. So this is actually a distribution of the possible outcomes. We are never certain. Everything is done using probabilities. So now the question is, how did we choose those vectors? These are the features you want to learn. So if you want to build your classifier, the features you care about are those vectors, the points you should be looking at to give you the best decision. And the intuition is the following. Look at me. Why is this a hand? It's a hand because it's a skinny object surrounded by stuff which is far away, by the blackboard, right? So if you look at pixels around up or down or left, up and down or left or right, maybe they will be far away from the pixels in my hand. Whereas the chest is a wider object, right? So if you look at nearby pixels, they will also be at the same depth, right? But the border of the chest, some pixels to the left will be close in depth, the same depth, the other pixels will be far away. So this will tell you the local neighborhood, the local topology of the neighborhood of the pixel you're trying to classify. That's the idea. But you don't know what to look for. So what you try is you try a lot of random possibilities. And it turns out that the accuracy increases with the number of images. This is a log scale up to 1 million images. It's not very high. This is accuracy per pixel. But remember, pixels don't have to be perfect. And then they also increase with the depth of the tree and with the number of images. But the one point I want to make is that to reach this point, for example, it takes 24 hours on an 8-core machine, which runs fully utilized. And this is a bad accuracy. You want to go to a higher accuracy. So the solution is actually to train with a lot of examples and to build very large trees. And these trees are actually, it turns out the decision trees are almost full. They are very dense. And the number of nodes in a tree is exponential with the depth. So if you go up to depth 20, you will have almost 2 to the 20 nodes in a tree. So it's a relatively large object. So that's why what we did was we implemented this in DryadLINQ. And it's a very nice DryadLINQ program. The initial program was quite clean, actually. It does a lot of histograms. And, but then we had to tune it because we reached all the targets that they set, and they said, oh, we want higher accuracy, we want bigger trees. And every time they increase the complexity, the complexity doubles. So it's very easy to overwhelm any cluster size you have. So this is essentially what we wrote. We used all the layers of the stack I described. We used the distributed storage where the images were laid out. Then we used Dryad to run these computations. The program was a DryadLINQ program, and we wrote a machine learning library. We didn't use much from the library. This is like a 30,000 line C# program. So one nice thing about this whole stack. And then finally, we actually train a decision forest, not just a decision tree. We train multiple trees because they are trained on different random subsets of the images. Apparently, they reduced bias. So one nice thing about the LINQ is because it's embedded in C#, you can write only one big program. And that program can spawn multiple computations, as you've seen. The program I just ran for you, running live, was spawning lots of computation. And it was very efficient. And I see I'm running out of time, so please give me a few more minutes to close the presentation. All right? This is all I had to do. But this is the core. This is just the final explanation. So when I was younger, I was very enthusiastic about computers, as maybe many of you are. I hope you are. Otherwise, you shouldn't be here. And I thought all the cool things have happened in the 60s. So this is a list of things that happened in the 1960s. So the IBM OS 360, virtual memory, Unix. This is actually Ken Thompson and Dennis Ritchie. Actually, I was on the internet, Bell Labs. I got to meet them. And this is Space Wars, the first computer game. This is the first mouse. This is the ARPANET, 68. Lisp, Multics. The ASCII code, I think, was defined then. So the PDP-8, it was a really cool time. I said, what the hell? Everything we're using today is the same. Nothing has changed. It's just bigger. So I was very sad. I was very sad because now I'm here, I'm in the 2010s, and I have nothing to invent. The world is so boring. But it turns out there's something special happening these days. And this is the cloud. Actually, the cloud is happening these days. And the cloud is actually humongous. If you haven't seen a cloud, you should see a cloud. I don't know if tomorrow at Yandex they will show us a cloud, but they do have a cloud of their own. The cloud is very spectacular, and it's something special. So the cloud really is what's different. The cloud is fundamentally different from what people have done in the 60s. It's a very large distributed system, and it has a lot of layers. I've given some examples. It's not structured so nicely. It's not like a sliced cucumber. It's much messier, but there's a lot of stuff to be built. So you could see what we want to build now is really an operating system for the cloud, and it's a race. So if you look out there, actually, there's a lot of companies. Each of them has built a little piece of that cloud. Some have done some parts, some have. Nobody has a complete solution, and maybe there's no universal solution. Maybe the solution will be the union of all these. I don't know. So there's many other companies. It's just a sample, all right? And the point is that in this lecture, I only showed you a little piece of the puzzle. There's many other interesting things. I talked briefly about lots of layers, but there's other stuff, and it's very interesting, very spectacular. So I urge you to learn about all the pieces, and that's what some of the other lecturers are doing. They're teaching you about other pieces, but there's many more. So the cloud today is maybe the last chance to do something interesting in computing. I actually don't know. Maybe there will be some other cool stuff, maybe quantum. I have no idea. But the cloud is really an interesting time. It's evolving very rapidly. Every year, there's a lot of literature. So the frontiers are being conquered. We invent a lot of new stuff, and the face of computing will change forever. Your children will know a different world than we know it today, all right? So you're seeing how this is being born. And we still have a lot of stuff to do. And the cool thing is that, I apologize for Uncle Sam. I don't know if you have an equivalent in Russia. But the point is, you might be able to do some of this stuff. So I think we are all very lucky. We are very lucky to be around here because at this time, it's as cool as the 60s. So these guys didn't do everything. We can do some of it. All right? So to summarize what I've told you, I've showed you in this lecture how you can build a set of software layers, and you can put them together, and I really showed you how you can use them to program large computers. I've run it on small computers. I run it on 16 machines, but Dryad actually runs in production at Bing. They have maybe 100,000 computers. I don't know how many they have, frankly. It changes every day anyway. So these systems can be very large, and they can do a lot of stuff. So this is my message for you. That's all I had to say. And then we can have a break. Thank you. I apologize.